the structure of the singular set of area minimizing curtains. So thank you very much for being here.
Thank you. It's a pleasure actually to be here. It's my first time. And without further ado, let me first start telling you what are area minimizing integral currents. So first of all, let me define for you what are integral currents. Okay, so the concept of a current actually was introduced by Daran, I believe, just a bit after the Second World War. And so a current is a linear functional on smooth, compactly supported differential forms. Okay, so of course I should tell you that these are maybe M forms. Let's see if this works. And so this will give then the notion of an M-dimensional current. And for the time being, let me just assume that we are in the Euclidean space. Okay, so in particular, I will try to stick to the notation that M is the dimension of the form and N is its codimension. Okay? So later on, I will also tell you that actually I'm going to look at currents which are inside a Riemannian manifold. I'm just going to do something which is really suboptimal and it's kind of dirty, but when I'm thinking about being in a Riemannian manifold, I actually think of a Riemannian manifold which is already sitting in some large Euclidean space, which I can assume by mentioning that in theorem. And then for a current to be inside the Riemannian manifold, it just means that the current vanishes if the form is supported outside of that manifold. Okay? In that way, I don't need actually to discuss about charts and things like that. Okay, so what was the purpose of this? Well, the purpose, of course, was to kind of generalize m-dimensional surfaces oriented surfaces, because if sigma is an oriented m-dimensional surface, what I can do is I can integrate the form over it. Okay, so I understand that for the action of the surface on the form by the integration as defining a current. Okay, very well. So there's one thing, of course, that you might anyway notice, and that is that, well, this is certainly fine, but the other thing that I can do is I can actually put a number over here, a real number, and this still gives me actually a functional. And I could do actually even a more complicated thing. I can actually decide for any weight that you give me a smooth function on sigma, which is taking values in R, and I can actually integrate against that weight. Okay? And then you start seeing that my generalization of this m-dimensional surface leads to something to be desired. Okay? So that's why Federer and Fleming introduced in the 60s integral rectifiable currents. Okay, so certainly nobody would object too much if as a generalization of my concept of, say, surface, I allow you to take a linear combination of smooth surfaces and count them with integral multiplicities. All right. The idea would be that instead of integrating omega against a fixed surface sigma, I actually allow to take coefficients alpha I and then integration over sigma I of your omega. Okay, and sigma I now are C1 surfaces. Okay, but I actually go one step further. Instead of allowing you to take actually a finite linear combination, I allow you to take a series. And at this point, instead of integrating over sigma I, the C1 surface, I allow you actually to integrate over some Lebesgue measurable subset of that surface. And in fact, because I can always approximate Lebesgue measurable sets with closed sets, I actually allow you to integrate over subsets which are closed. Okay, so that actually doesn't guarantee you that this series is converging. So to guarantee you that actually this series is converging, I'm going to assume the following. And the assumption is that if I take the series of the absolute values of these coefficients alpha I times the n-dimensional volume of this species ei, then I get something which is finite. So this series is converging. Okay, so here I should specify anyway the alpha i's. Okay, so this is what I will call an integral rectifiable current, and actually you could imagine that this thing over here is a good substitute for the generalized volume of your current, which we will call mass. That is true only if you pay some attention, right? So in the way I've actually written over here, I could make, for instance, the same set appear twice, for instance, with a positive sign and with a negative sign. And then if I actually compute the mass in this way, I might write, I don't know, a surface as twice the surface minus the same surface, and I actually get a volume which is 3 times that surface. So that I don't want to do. So this is really going to be the mass of my current under the assumption that these Ei's are piecewise disjoint, pairwise disjoint. And without loss of generality, you can believe me that this you can assume. Okay, so these are integral rectifiable currents, but in fact, integral currents are currents with the property that both the current and its boundary have that structure. So they can be represented in this way. I should tell you what is the boundary of a current. The boundary of a current is defined, even in de Rham's original theory, by postulating Stokes' theorem. Okay, so the boundary of a current acting on a form is the same as the current acting on the differential of the form. Very well, so why all of this is interesting? Well, all of this is interesting because you can actually do two things which are kind of interesting for variational purposes. And this is part of the Federer and Fleming theory. So you can solve the oriented plateau problem in the Euclidean space, for instance. Or you can represent any integral homology class in a compact closed Riemannian manifold, an integral homology class with a minimizer of that mass. Okay, so this is part of the theory of Federer and Fleming, which in fact generalizes the theory of sets of finite perimeter by De Giorgi to higher codimension. So the first one is that so you can solve the oriented plateau problem applying the direct methods of the calculus of variations. So this means fix some contour gamma, which actually you can assume is a nice surface without boundary. Okay, then there exists a current T with boundary of this current equal to, it has to be oriented, of course, with boundary of density equal to gamma, the action of gamma as a current is usually denoted in this way, which minimizes the mass. More in general, so if, say, M is a smooth M plus N dimensional Riemannian manifold, any integral homology class of M can be represented by a minimizer among integral currents in that homology class. So one thing that I actually should say is that part of the theory of Federer and Fleming is that by using these integral currents, you can really recover the usual integral homology, for instance, the same homology that you define using singular homology. Okay, so because the theory satisfies the axioms of Eilenberg-MacLane. So, okay, let me just say here, every homology class linear manifold has a representative of this class. So now you could also ask the question, so well, I've introduced actually this kind of generalized situation, but maybe at the beginning of the statement of the Plateau problem, what I'm really interested in is like, you give me a smooth boundary. I'm actually interested in smooth surfaces with that boundary and on minimizing my area inside that class. That one is not a compact class. So if I try to actually prove that there exists a minimizer by using the direct methods of the calculus variations, I will in fact fail. But you could ask whether I'm introducing an undesired object over here, because this thing is more general. So there is something which is called the deformation lemma, which tells you that you can reasonably approximate any integral currents essentially with polyhedra. Now, there's still a catch if you want to work in the smooth category, right? So famously, there are, for instance, homology classes. So this is famous work of René Thom in the 50s that cannot be represented by something smooth. And so then that cannot be a minimizer in the class of smooth representatives simply because they don't exist. So there's still something interesting, which is just something we actually completed right in the last couple of months. So this theorem was actually announced by Almgren and Brauder in the 80s, but they never published a proof. And so together with Gianmarco Caldini, and by talking actually to Bill Brauder, we actually managed to complete an argument for this theorem. So the theorem says that, so if, say, this class Hm of M can be represented by a smooth submanifold, then any current, any integral current which is representing this homology class can actually be approximated by smooth submanifolds whose area is converging to the area. Okay. So let me just say it over here. So then every integral current in that homology class can be approximated in volume by smooth objects. By smooth in the same homology class, of course. So this actually tells you that if you try to take the infimum over all smooth surfaces, you can hope even there is a minimum somehow. well, then this coincides with the minimum of the mass as constructed by your theory. So you can think about this as some sort of relaxation of the variational problem in which you're actually trying to minimize among smooth objects. Okay, so what's going to be the subject of the talk? So the subject of the talk is going to be whether these minimizers, whether they are minimizers of the oriented plateau problem or representative minimizers which are representing some homology class in some Riemann and some manifold, whether they are regular in the case of the plateau problem when I'm staying away from the boundary. It's really an analysis problem and it's really a local problem. So you can just think that you're focusing on some point which you have defined in some way, which is in the interior of that current. So away from the boundary, you can assume the boundary is smooth or the boundary does not exist as if you were representing an homology class. And you're just like, you know, putting a small ball around that point and you're asking yourself whether this minimality property forces you to be more regular than the general definition that I've given you with this kind of, you know, countable number of kind of ugly pieces of C1 submanifold. So here it's, so that's what we call the interior regularity problem. And it's well known that minimizers can in fact be singular. And there are two very famous examples, and I'm just going to actually give you the first example for historical reasons, but that's not what I will focus upon. And then I'm going to give you a second example, and that's going to be the focus of most of my talk. So example one is the following. So take, so in R8, which I'm going to write as R4 times R4, with coordinates, say, x, y. So take sigma to be xy such that modulus of x is equal to modulus of y. Okay, so this, if you intersect it with the unit sphere in R8, you're actually going to have the product of two three-dimensional spheres. And what you're doing is you're taking the product of these three-dimensional spheres and you're making a cone with the origin, okay? So of course this is a cone with a singularity at the tip of the cone, right? I mean, because if you're smooth at the tip of the cone, then you're forced actually to be a hyperplane, okay? So it's a cone with a singularity at the origin. It is smooth outside. And it is an absolute minimizer among all smooth surfaces if you cut out, say, a portion of sigma with the sphere of radius 1. So you cut out with the sphere of radius 1 your portion of sigma, you get this S3 times S3, you have a legitimate boundary to solve the plateau problem, and among all oriented surfaces which are smooth, you want to find a minimizer, okay? There's no minimizer. Any minimizing sequence is actually going to converge to this guy. This guy is then a minimizer in the sense of currents, which I told you. And not only it is a minimizer, it is the minimizer. There's no other guy which actually achieves that mass, that volume, with that given boundary. So in some sense, it's an unavoidable singularity. Okay? So, and this is a famous theorem by Bombieri, De Giorgi, and Giusti. So let me just summarize what I told you by saying sigma is area minimizing. But it's in fact much better than that. Because it's kind of unique area minimizing if you're only perturbing with something which is compactly supported. So that sort of coincides with it outside of a large book. Very well, so you see, of course, that this guy is a 7-dimensional hypersurface in R8, and it has a point singularity, right? So you cannot hope that your minimizer, even in the case of hypersurfaces, is always there. Okay, but this is going to be example number 2, and this is going to be for us more interesting. I mean, that is bloody interesting, actually, but for the reasons that we would see further down, this is going to have some more inputs. So let us look at the following algebraic curve. So here Z and W are complex variables. Okay, so this sits inside C2, which I'm going to regard as R4. So it is, except for the origin, which is again a singular point, this is a two-dimensional oriented surface in R4. And again, it is an absolute minimizer, and it is the unique minimizer as before. So now you cut it with a sphere of radius 1, and when you cut it with a sphere of radius 1, you actually get a very nice real analytic curve. It couldn't be better than that in terms of regularity. And if you minimize among all smooth surfaces with that particular curve in R4, there is no minimizer. Like it happened before, any minimizing sequence is converging to this guy, who happens to be the minimizer in the sense of integral currents, and who happens to be also the only minimizer in the sense of integral currents. Now, that this property holds for this particular algebraic curve is actually not a coincidence. In fact, the same property of being absolute minimizing, it works for any zero of any holomorphic function in arbitrary dimension on the complex space. In fact, it's much more general. It works on Keller manifolds as well. So it gives you a huge amount of examples of minimizers. In particular, like, if you take algebraic geometry and you take your favorite, I don't know, projective variety, for instance, you will get plenty of homology classes with plenty of representatives which are going to be singular, okay? And the fact that this guy is minimizing, or that all holomorphic subvarieties of a Keller manifold are minimizers, in integral currents is actually a theorem of Federer, but really there is a fundamental computation in complex differential geometry behind this, and this is an old computation by Wirtinger. Well, I mean, the theorem of Federer is old, but the computation of Wirtinger is older. Very well, so you got your answer. So if you were hoping that there are minimizers which are smooth, there are not. And it's not like I'm cheating. Like in the category of smooth surfaces, so smooth oriented surfaces, you will not find a minimizer in these cases. So your singularity is kind of really forced upon you. You take a minimizing sequence and you will converge towards that guy. Which besides is one of the power of this theory, that you can get to this conclusion in these examples. The interesting conclusion of, say, decades of hard analysis work is that these examples are optimal. So they really identify the worst situations that can happen. Okay, so here is the theorem that I want to illustrate to you. So there's two different situations. So codimension 1. So we are in codimension 1, and let us just focus on the case of the Euclidean ambient space. So on a Riemannian manifold, all I'm going to tell you is correctly, is still true, and you just need to actually assume that your Riemannian metric is sufficiently smooth. C3, something like that, actually suffices. So if the codimension n equal 1, an n-dimensional area minimizing integral currents is regular. And so by regular, I mean locally, when you integrate, say, a form which is compactly supported in some nice domain, really your current is represented by the integral over a submanifold times an integral multiplicity. Okay? So the best you can actually hope. So is regular a way from a closed set of dimension n minus 7. Okay? So in particular, until you're actually at this eight-dimensional Euclidean space, so if you were trying to do something like the Bombieri de Giorgi Giusti example in R7, you're not going to get it. Like, you know, you start with a smooth, nice boundary, you find a minimizer, which is actually smooth. It's a classical one, the one that you would get if you're minimizing among smooth-oriented circles. But when actually m equals 7, this becomes 0, and so you can actually get point singularities. Okay? So in fact, the singular set is n minus 7 rectifiable. Okay, so now what does it mean n minus 7 rectifiable? N minus 7 rectifiable is kind of a measure theoretic substitute for saying that it is an n minus 7 submanifold, which is not something you can completely hope. I mean, you can actually imagine there's going to be, for instance, if you go to an 8-dimensional minimizer, that you might actually find a structure of singularities which are like one-dimensional arcs, which might meet actually at some point. I mean, it might have some tree structure. And you can actually make examples where that happens. So rectifiable means up to a set of measure 0. In this measure, you can actually cover with countably many C1 surfaces. It's kind of already what was hidden behind the notion of an integer rectifiable current. So the reason why it is called integer rectifiable current is because if you look at the union of these species Ei's, well, they are inside the sigma I's. The sigma I's gives you the countable cover of your set. So it's not quite as satisfactory as being C1, but it's at least better than being a general kind of set of dimension n minus 7. So it's particularly interesting in 0 dimension. So in 0 dimension, it actually tells you that the singularities are countable. But in fact, you can prove a little bit more. Actually, when m is equal 7, you really can prove that the singularities are isolated. So now a 0-dimensional set, on the other hand, you can make it as an exercise, or maybe you saw this, can be an uncountable set. Okay? It could be like a counter set of dimension 0. So you can easily construct it. So even though it doesn't seem actually much, it's a great improvement from just telling you that it has the correct Hausdorff dimension. So here when I'm talking about dimension, I'm talking really about Hausdorff dimension. Okay, and the other portion of the theorem, which is actually what I'm going to focus on, is that if the codimension n is bigger or equal than 2, then of course even surfaces can have singularities, but the same is true if I substitute m minus 7 with m minus 2. Okay? In other words, if I am in the case, which is really lucky, of surfaces, I will have point singularities, and in fact, isolated point singularities. And if I am above, say for instance, if I am 3, then I have a one-dimensional set which kind of looks a little bit like a C1 submanifold, kind of. I can cover with countably many C1 surfaces. And actually, the statement is for sure optimal, meaning a student of mine, Jinhua Liu, has been able to construct minimizers in Riemannian manifolds, minimizers for which you have actually fractal singularities of dimension which is below m minus 2. It's not a counterexample to this because this rectifiability would kind of ignore sets which are null for the n minus 2 dimensional measure. And these examples have some sort of fractal dimension which is between m minus 2 and m minus 3, for instance. There's some indication that the theorem is likely optimal even in codimension n equal 1. So there's an excellent recent work by Leon Simon in which he constructs stable minima surfaces with fractal singularities. So there's a stable meaning the second variation is positive, so they're stationary. The first variation is equal to 0. The second variation is positive. You could imagine they might be like, some sort of local minima, but you are in an infinite dimensional context that is actually not so easy to prove, in fact. And of course, that they are absolute minima, that is typically a very hard thing to show. Okay, so now I'm not attributing the theorem to somebody, so let me actually start with the attributions. So the dimensional estimate is a famous result in the 70s. So Federer got to that particular theorem in the way I told you, but this was built up on previous results by De Giorgi, Fleming, Almgren, and Jim Simons. And so they came all together, and that was kind of fun. So the rectifiability is another famous result in the 90s by Leon Simon. And in fact, this result was proved not so long ago by Neighbor and Valtorta, who actually showed that the singularity is not only rectifiable, but it also has finite n-7 dimensional volume. That is a very interesting additional information, because the rectifiability only tells you can cover with countably many. It doesn't tell you that the thing that you're covering has finite volume, right? I mean, because you could sum countably many infinities. Okay, so so this is going to be, so this work by Neighbor and Valtorta is actually going to be very important for what I'm going to say, which is mostly focused on the second case. Okay, so how about the second case? Well, for the second case, so this is what I'm actually going to focus on. So the case m bigger or equal than 2, the dimension estimate is a famous work by Almgren that he completed at the end of the 70s, and so I think typically we cite it as a result from 1980. I mean, there was an announcement. So, but this thing was, at the time in which it was published, it was a 1728 pages proof. Okay, which I think is fair to say nobody really checked, as far as I know. Okay, so here he didn't prove actually the rectifiability. He didn't prove the rectifiability in there, which is the second part of the theorem. So, but Chung, in 1988, proved that if m is equal to, the singularities are isolated. Okay, so Chung proved this, but there's a caveat. So because it's a fairly long paper, and you need, I mean, he has a certain starting point. And that starting point is actually handled in the appendix. And in the appendix, it says, like, okay, you don't have to read all of 1728 pages. You can kind of dispense of the last couple of hundreds. But what is actually contained up until, like, I don't know, page 1500, something you've got to modify in a certain way, which can be done. It will give you some object, and by starting, like, that object exists, then I'm going to show you actually this result. Okay, so this theory, so this regularity theory was actually a subject of intense study by myself and Emanuele Spadaro in like around 2010. So we published 5 papers in which we are actually recasting this theory in a much more manageable way. So there's many of the, so some of the fundamental ideas of the book are actually the same in our work, but our work actually introduces new idea that makes this proof much more manageable. And building on this, in a subsequent joint work with Lucas Pollard, I believe this is like around 2016, we can actually give you a proof of what is missing over here, of like, the starting step after which you can actually apply his argument and complete the fact that the singular set is isolated. Okay? And I mean, in some sense, it's no surprise because we have a much more manageable theory over here that we can actually deal with what he was telling you. Okay, you have to go through the whole book and then, make some adjustments and construct this object. I'm actually going to tell you to mention what this object is. Okay, so what about actually the general rectifiability? So the general rectifiability is a theorem which was proved last year by two groups. So n bigger than 2 and rectifiability. So there's two groups. So myself, Minter, and Skorobogatova. So we posted 3 papers on the archive in 2023. And at the same time, Kraml and Vikramasekera posted 2 papers on the archive and announced the third one in which that proof would be completed. And I mean, there are different proofs, but there are actually quite a few points which are in common between the 2 approaches. So both, actually, interesting enough, are sort of 3 papers, but there's quite an interesting subdivision of what probably looked harder to us than what actually looks harder to them, meaning that apparently what we actually could complete was probably what for them was kind of the path that they started. Okay. I'm not going to give you, so now I have like 20 minutes to complete this talk. I'm not going to give you a comparison between the 2 because that would be extremely hard. I'm not going to give you proof because that would also be extremely hard, but I want to give you a feeling for, well, first of all, why is it so bloody long? So why did it take actually 1,700 pages to Almgren? What is the challenge that you're actually kind of facing when you want to try and prove a dimension bound? And then secondly, what have we done which allows us actually to get to the rectifiability, which was considered sort of, for interior regularity, the biggest open problem in this particular subject. Okay, so that's what I'm trying to do. Now, so let me go back to the examples of singularities, which I gave you maybe 15, 20 minutes ago. Okay, so if you remember example 1, so this one was modulus of x equal modulus of y, with xy in R4 times R4. That was one example, and this was the codimension 1 example, so the famous example that was proved by Bombieri, De Giorgi, and Giusti, that it is minimizing. By the way, it actually goes under the name of Simon's cone because it was actually it was dug out by Jim Simons in his work, which helped actually getting the regularity theory as the first obstruction to kind of get regularity in dimension higher than 7. And it's a real obstruction. And the other one, which was discussed, Okay, so you see something actually very interesting, that if you apply homotheties, I mean, if you center yourself at a singular point in zero, and you kind of escape the current, right? You apply homotheties, this cone stays the same. I mean, it's a cone, so if you scale a cone, you actually keep being a cone. But if you scale this guy, right, so if you apply a scaling like lambda z, lambda w, and you let your lambda converge to, to 0 or to plus infinity, if you want to go to 0, you have to make it converge to plus infinity, actually, you will see that there is a dishomogeneity over here. So you will have like lambda squared z squared is equal lambda cubed w to the power 3. I mean, like you divide by this lambda, which is going to infinity, and one of the two coordinates disappears. And you actually converge to what? To w equals 0. So you actually converge to a plane, okay? So why is it this interesting? Well, first of all, there's a general fact, which if you read the literature, apparently the first one to notice seems to be the Giorgi. There is a monotonicity formula that actually tells you the following. If you have an area minimizing object, even though your object, probably sucks from the point of view of regularity, you don't have any information, maybe it's really, really bad. When you're actually applying homotheties centered at the point, you will converge to a cone, because the ratio between the volume inside the ball of radius r and the natural scaling of the volume of an n-dimensional disk is actually monotone. It's called the monotonicity formula. So this allows you, I mean, this is very exciting for an analyst. Why is this very exciting? Because you focus yourself, for instance, say you're two-dimensional. You focus yourself at some point where you want to analyze this object. Right? You make this rescaling. You've got compactness, because your theory allows you for compactness. You make this rescaling, and you converge to a cone. Now, that cone, you're going to prove it's area minimizing too, because being minimizer is steep and stable. I mean, if the cone is not minimizing in the limit, then you can possibly lower the area even for some of the dimension. Now, why is this exciting for you that it is a cone? Well, because before you had a two-dimensional surface. Now you have a two-dimensional surface, which is a cone. The cross-section is a one-dimensional guy. And an ODE is typically easier to solve than PDE. So you have a one-dimensional object to analyze, maybe you can classify. Okay? So you will see two basic differences between these two, right? So this guy is a conical singularity. This guy, actually in the limit, is not singular at all. It's like flat. Now, say that I was kind of a naive person, and I was like, somewhere in one of these points, and I would hope for the following conjecture. I make my rescalings, and if my rescaling is converging to a plane in the limit, I see the tangent plane to a regular guy, right? I mean, it's a plausible conjecture. And if instead I see something which is singular, then, okay, I've got a singular point, right? I mean, because if I were smooth. So, between codimension 1 and higher codimensions, so this fact that the singularity can actually happen at a point where what we call a blow-up, or what we call a tangent cone, is flat, this can only happen in codimension bigger than 1. Because in codimension 1, there's a very powerful theorem. It's maybe the father of all epsilon regularity theorems in geometric analysis, which was proved by the Giorgi, that tells you that if the tangent is flat, in this case, then the surface is flat. I mean, the surface is smooth. So you completely identify your singular points by taking rescalings and finding singular cones in the limit. Okay, so this makes your life much, much easier. In particular, it's because there are no area minimizing cones before you hit this dimension 7, which is what Simons proved, that your singularity has codimension 7. And it's a relatively soft covering argument using the monotonicity formula. It's bloody hard to prove rectifiability. So Leon Simons' proof is very hard. And Daniel's and Aaron's proof actually was wonderful because it's much more flexible and it uses much more the nature of the monotonicity formula to actually prove this rectifiability, which means it's extremely flexible. You can actually use it in plenty of places. Okay. So that accounts for the difference between the two, but what the hell do you do over here? Okay? Well, you have points where plausibly you make a rescaling, you converge towards something flat, and that flat is a plane, and so your singularity has disappeared in the limit, which is a very bad news. But actually, there are much worse news, because I could do something nasty like this. Now, if you look at this guy, like, you know, you can't take the square root because the square root is not uniquely defined, but, you know, you're going to get some sort of multi-valued function if you take the square roots, because there are two square roots outside of the origin. So your surface looks very much like this. And you see, that's a code which is perfectly regular, right? This one is actually the one responsible for the singularities. I mean, not only a rescaling by an homotopy would just scale this guy, would put it equal to 0. But even if I try a parabolic rescaling, that it means I try to rescale the z coordinates by lambda, and the other coordinate by lambda square, which I don't know I can do. Huh? I mean, when I'm actually rescaling by an homotopy, I keep the minimizing property. But when I'm scaling actually the two factors in a different way, God knows what is going to happen. Okay? But to actually kill this thing over here, I need to understand that at the order 1012, actually, there's still something smooth before I finally see the singularity, right? So here's like your W to the 1012, and on top of it, there is a branching, but the branching looks like this. You probably can't see it down there, right? That it is different from the red. It's done on purpose. Okay, so what is actually Algren's theory trying to do? Okay, so let me give you a very quick... by the way, maybe before I actually go on, let me make a comment for PDE people, okay? So for PDE people, while the Giorgi's theorem is an actual epsilon regularity theorem, I'm sufficiently close to some model that is smooth, then I'm smooth. This theorem over here looks like I want to actually capture a first non-trivial order, okay, in the Taylor expansion of some solution of some PDE, okay? In other words, I maybe would like to actually tell you that if I have a solution to this PDE which is vanishing at infinite order, actually the solution is identically equal to 0. That is a very famous problem in PDE, and it's called unique continuation for the partial differential equation. And so the theorem has two completely different natures. I mean, the one regularity theorem is an epsilon regularity theorem. It's kind of a perturbation argument around the state, which is nice, possibly a linearization. The other one is way far from that. You actually have to capture a first non-trivial order, and this is typically what you actually do, but in unique continuation theory. Okay, so from the pioneering work of Carlo. Okay, so what is actually Algren's theory, and why is it so difficult to implement it? Okay, so first of all, step one in Algren's theory, which is what really work in the papers with Emanuele. So this is really a roadmap that we take as well. So first of all, one of the main players in trying to understand the epsilon regularity theory of de Giorgi is to approximate your current, when it is very close to a plane, with the graph of a function. And, you know, if you're solving the minimal surface equation with the graph of a function, and your function has very little gradient, actually that function is very close to be harmonic. And harmonic functions we understand very well. So the first thing you would like to do is approximate sufficiently flat minimizers with harmonic functions. But you can't actually do it, because if you remember my example, close to the singularity is nowhere a classical function, but it's a multi-valued function. And actually, the fact that it's multi-valued allows you to understand how many values you need. Because it's a kind of a cover of a plane, and the values that you need depends on, at this point, how much mass you actually have, right? I mean, if you're a double cover of the plane, asymptotically, you're actually going to look at twice a disk, okay? So what you actually want to do is approximate with harmonic multi-valued functions. But they're really minimizers of the Dirichlet energy. There's a subtle difference over here, because when you actually take a suitable theory of multifunctions, you will realize that your space is not linear. Okay, so now there's a part of this which is constructing a suitable Sobolev, minimizing and so on, but these guys, they are also singular. So how do you analyze the singularities of this guy? So here there's a basic insight by Andren, so this is a genius idea. So there's a quantity which is called frequency function, which is monotone, and allows you to analyze singular points, or allows you actually to sort of Taylor expand multifunctions. Okay, so now this is really kind of step 1 and 2 actually. Because there's a first step in which you have actually to kind of construct a theory of Dirichlet minimizers which are multi-valued, and then you actually have to know how to approximate something which is sufficiently flat. But it's not going to be enough, and the reason why it's not going to be enough is because if I run a kind of argument like that by sort of approximating this guy from a plane, I will actually not be able really to distinguish this red guy from these two kind of green ones. The green ones are just a very, very high order perturbation of something which is small. So there's something else which I need to do, and I need to actually capture sort of the smooth part. And the reason why I'm actually able to capture it is because it is, very approximately, but it is an average of the sheets. So this is what is called constructing a center manifold in Andren's theory. And in a sense, this is what we really did, we, meaning Emanuele and I, do most efficiently. So this is more than half of the book, actually, constructing this object. So in our realization of the theory, it's a single paper. I mean, it's a complicated single paper, but it's around 50, 60 pages construction. So it's not let's say it's a quarter, actually, of the whole program. Now, once you actually capture the smooth part, you want to approximate, again with a multifunction, but on the normal bundle of this object. What is very difficult to do is actually to get this object smooth enough so that I can approximate on the normal bundle, and accurate enough, right? So in particular, there's the following funny phenomenon. If you know that this guy collapsed, our kind of center manifold would have actually to coincide with the collapsed surface. And you would get immediately higher regularity for your surface without going through Schauder estimates, which is like what you do in the George's theory. Okay, so you capture the smooth part, you construct this center manifold, and at this point you have, on the normal bundle your multifunction. Now you're actually able to kind of approximate again on the normal bundle and capture this part of the expansion. So capture really the singular part of the expansion. And the reason why you will be able to actually capture this approximate part, you will be able to capture somehow the singularity is again because there is this monotone quantity. This monotone quantity really works magic because this monotone quantity allows you to compute this exponent over here. And it tells you what you have to normalize with to actually find a non-trivial limit, which is, what was a mystery at the beginning while you're trying to build up this thing. Okay, so now why do you actually end up with the dimension estimate? You end up with a dimension estimate because these building blocks, which are singular, they have a certain homogeneity, and you're not able to actually pack too many of them together, right? Because they have essentially a one homogeneity. So if there's a singular point over here, there's a singular point over there. If you are homogeneous with respect to both of them, then you actually have to be a function of the orthogonal variable, okay? And then you have like a one-dimensional function. And the one-dimensional function is easy to describe. It's easy to compute, and just to show that you cannot be singular on, say, a codimension 1 set. So that is kind of the heart of the matter. Okay, so how do you get to rectifiability at this point? Well, so first of all, that was a paper by myself, Andrea Marchese, Emanuele Spadaro, and Daniele. So, okay, so step one is actually to get Daniele, and he explains this to you how his work with Aaron Neighbor works. And as I told you, it's really using the monotonicity formula for minimal surfaces in an effective way. And this frequency function is actually monotone. So what we discover is that there are similar computations, similar structures that you can use in an effective way, and now prove the rectifiability of the singular set for the linear model, so for the big minimizers. So this was back in 2018. Okay, so now you would like actually to run the same now, like, you know, step 2, 3, 4 by actually leveraging this thing that we got at the linear level, but becomes much more difficult. And the reason why it becomes much more difficult is that you have to face a very big enemy. So that center manifold that we have constructed kind of varies from point to point. And so when I want to study something global, I might actually end up on functions which are defined on different quantities, on different objects. So there's two situations. One is a lucky situation. So you've got a bunch of singular points, and there is a single center manifold for some reason which is passing through all of them. Okay, that's not very likely, but it might happen. And there is like that with in one paper. And there's the other thing in which actually these things sort of start changing and hopping around. And one of the things you realize is that while you're actually solving this problem, you have, if you want to follow this route, solve another kind of long-standing open question, and that is whether, when the tangent cone is flat, that tangent cone is actually unique, at least up to a set of n-2 dimensional measure 0. So you can do that, and so this is what we're actually doing in the paper with Minter and Skorobogatova. But so let me just tell you that there's a great, well, great, I shouldn't say this. But I mean, it's something that we are very proud of. So an important new hub estimate, which wasn't known before, and this is what I'm going to leave you with. And this estimate appears in the work of Kramel and Wickermann-Sekera as well. So it's some sort of L2 and infinity estimate in the context of currents. So this L2 and infinity estimate says the following. So if you, with respect to a plane, you have your current, which looks like a branched cover somehow, sort of approximately, and you assume that the L2 distance to this plane is sufficiently small, then of course, you know, it could be, and this would be the usual L infinity estimate, that there's a slab, so sort of this one is the square root of the L2 distance, and actually your current is all sitting over here. So this would be a typical kind of L infinity L2 estimate for an elliptic PDE. But because you have a multi-valued function, there's also another situation that you might imagine, and that is that, you know, So there's another slab over here, and there's some space in here. Okay, so it's not really an L2, L infinity estimate with the L2 distance to the plane, but with what is called kind of the tilt excess. And the tilt excess is an L2 computation on how the planes are kind of skewed compared to kind of the orthogonal plane. So you compute kind of the angle between the planes in your current, you integrate over the whole current, and you get a certain number, let us call it h. Then the estimate tells you there's slabs of size square root of h, in which all of the current is actually present, and there's nothing in between. So there might be maybe a very big space over here, but there's absolutely nothing in between. And that is maybe the most important estimate, actually, which is new in our work. And, well, I'm sorry I actually went a couple of minutes extra time. Yes.
But what if I change the boundary a bit? And does especially I imagine the tilting estimate, like, does it make it better?
Yes.
Does it allow
So,
to tell me, I imagine there are results in this direction, does the tilting estimate?
There are results in this direction. So, first of all, the first singularities that you encounter, the m minus 7, like, the zero-dimensional singularities, they would actually disappear if you perturb the boundary in a generic way. Okay, so this is a result by Smail, the son of the topologist, in the 80s for the hypersurfaces, and it's a kind of recent result by Brian White for the two-dimensional surfaces in higher codimension. Now there's a couple of recent papers by Chodosh and collaborators here. In the case of hypersurfaces, they're able to show you that this happens also for, say, 8-dimensional and 9-dimensional surfaces in R9 and R10. So you perturb the boundary data, and actually the surface becomes smooth. And then it's an open problem. It's a very interesting open problem. For instance, if you were able to settle this problem, you probably would be able to prove the positive mass theorem in any dimension, or I mean the Chenyard theorem in a very clean way, which is a kind of massive problem. Now, in higher codimension, situation is actually trickier. So there are singularities that don't disappear. So in particular, this is something that at the level of cones was discovered by Lolo back in the 80s. So it's in his PhD thesis. So you can get situations in which you see a self-intersection of your surface, and you're actually not able to perturb the self-intersection away. And now the same student that has the examples of flat singularities has actually examples in homology classes. So there will be kind of Riemannian manifolds with an open set of metrics, some homology class, there's a representative, that representative has a singularity. You perturb the metric a little bit, which is akin to kind of like, moving the boundary, and actually the singularity persists. You're actually not able to make it go away. Still, one could argue that it's not a definitive counterexample because the surface is not embedded, but it's immersed. So it really kind of like, decouples in a couple of graphs, which are very nice and smooth, but they meet at some points. And what you're not able to do is you're able to perturb away these self-intersections. Even though, so this is of course the magic. Dimensionally, there will be space to actually like, kind of get rid of the self-intersection, but you're not able to.
What you just said sounds very similar to issues in intersection theory in algebraic geometry, considering that your examples
Yeah, so the example comes from, like, the sort of examples before you actually put it in an Emanuel manifold. They actually come from special arrangements, special Lagrangian geometry. So yes, there's some important input from geometry in there. But so this guy is persistent even if you kind of get away from the, because your perturbation is arbitrary. So you maybe don't stay in the case of